the very first of our tricky graph problems I want to address is that of connectedness. So it's a pretty straightforward problem. Given a graph, does there exist a path from, say, vertex 0 to vertex 7? So I'm going to give you an algorithm that I'd like you to critique, which is the following. So if I want to check if, say, 0 and 7 are connected, we say, well, does 7 equal 0? In this case, no, right? 7 is not the same thing as 0. So what we could do then is check all of S's children for connectivity to T. And if any of those children is connected, we'll return true. So in this case, there's only one thing to check, which is 1. So we can say if connected, 1, 7 will return true. And in that case, if that does not happen, we'll return false because, well, none of my children was connected to T, therefore I'm not connected. So what I'd like you to do now is think, will this algorithm work? Turns out it won't. So the goal for you is to think, why won't it work? Okay, so ponder this question briefly. Okay. So the issue is that if we do this, right, if we think about what this code's going to do, what connected 1, 7, it's going to say, is 1 connected to 7? No. So then it'll check all of its children. It'll check, is 0 connected to 7? And is 2 connected to 7? And so forth. And so that can actually generate, in this case, an infinite number of calls. We can get into an infinite loop in the worst case. And in the best case, maybe it works, maybe it doesn't. You'd have to think more carefully. But it's going to be incredibly inefficient because we keep revisiting vertices over and over and over. So we want to avoid that problem. So what we're going to do is change things up just a little and say mark S. Then the magical step will be, rather than checking all of S's children or all of S's unmarked neighbors, all of S's neighbors, we're going to check only the unmarked ones. Okay. Now I realized, by the way, while I was mid-video, but I'm under a little time constraint now, so I won't quite get there, that we didn't introduce the term child at any point, but I hope the intention was clear, which is a neighbor. Okay. So let's now run through what this algorithm feels like if we mark vertices as we search. So what we're going to do is we'll start by, well, marking 0, and we'll say, is 0 equal to 7? No. Okay. Now we'll check the children, or the neighbors, I guess we'll say. And we'll say, is 1 marked? No. Okay, so in that case, we'll call connected 1, 7. Well, when you call connected 1, 7, the first thing you do is you mark 1. So I'm using this whited out square to indicate that we're marked, and I'm using this asterisk to indicate the value of S. So then we say, is S equal to 7? No. Is 0 marked? Yes. So in this case, we avoid the problem we had before of revisiting 0 again. And then how about is marked 2? Okay, well, it is not marked, so then we'll check connected to 7. So we go here. Okay, so now we mark 2. Is 2 equal to 7? No. Is 1 marked? Yes. Okay, is 5 marked? No. So then we'll check connected 5, 7. Okay, we end up here. Okay, at this point, we mark 5 and we say, is 5 equal to 7? No. Is 2 marked? Yes. Is 4 marked? No. So we'll check connectedness for 4 and 7. Okay. Now you and I, being animals that have a visual cortex and the ability to reason about space, we could tell this is a losing proposition, but the computer has no idea. So we'll check connected 4, 7. We end up here. Mark 4. Is 4 equal to 7? No. Okay, is 3 marked? No. Okay, well, we'll check connected 3, 7. In this case, well, there's no more children, so finally we'll return false because we know that 3 is definitely not connected to 7 because there's nowhere else to go. So since this is false, we go back to 4. There's no more children, so we return false. We get back up to 5. Well, in this case, 4 wasn't connected, but we still need to check 6 and 8 potentially. So we're going to keep checking our children because there's still some other hope. So then we say, is 6 marked? Okay, well, in that case, we'll check connected 6, 7. Is 6 equal to 7? No. Okay, is 5 marked? Yes, so we're not going to use that. Is 7 marked? No. Okay, well, then we'll check connectedness of 7 and 7. Yes, 7 equal to 7, so we'll return true. And then because this was true, we'll return true. And then because this was true, 5 has gotten a true, so it'll return true. 2 will return true. 1 will return true. And we get back to the beginning and find the answer is true. We did it. We found that 0 and 7 is connected, and that right there is one way to do connectedness. Now, there are many others, and you might have had some issue with the fact that we kind of went down this blind alley, but it turns out that this is a rather popular and powerful algorithm, and it's known as depth-first search, by the way. So this idea of exploring, and if we think about the process that we went through, this idea of exploring the entire subgraph for each child is known as depth-first traversal. So this graph makes it a little easier to see why this is true. That if we do a depth-first traversal, like we just did, on this graph, whenever we call connected on 1, we're going to explore all of 1's children, before we do any of the other children, 3, 4, 8, 7, right? So we're going to go all the way down this branch before we try any of the others. We actually did that there, right? Before, we were willing to do, so when we got to 5, right? Before we get to 6, we're going to explore this entire subgraph over here, and that's the essence of depth-first traversal. Now, depth-first traversal, I'm not one to usually do webcomic-y things in the middle of a lecture. It's kind of hacky, but I think this is a nice one. So depth-first traversal is something that you could apply to real life, and this comic here gives an idea of why depth-first traversal might not be the best idea. And it's true in real graphs too, and so this I think is a nice illustration. So imagine you're preparing for a date. Okay, so what do you need to think about for the date? Medical emergencies, dancing, the food's too expensive. Okay, well, let's first start with what kind of emergencies. Well, there could be a snake bite, lightning strike, you could fall from your chair. Can't quite read that. It's a challenge to the reader. Okay, well, what snakes are dangerous? Well, let's see, there's corn snakes, garter snakes, copperheads, and so forth. And eventually you find yourself reading about snake venoms, and you need a spreadsheet, okay? So that is depth first search. Well, I guess this is the punchline. Okay, whoops, I didn't know there was a punchline. I forgot. So, hey, you're not dressed yet. Well, you let them know, your date, that the deadliest snake is indeed this snake. And so in this case, depth first search may not be the most appropriate thing for preparing for dates, and that may be true for real computational problems as well. So how would we implement depth first search? Well, I'll mention that even though depth first search can run you into trouble, as we see here, it is still a common pattern in in real graph algorithms. And essentially, the way we're going to do this is kind of intriguing, right? Usually in the past, whenever you've been given a data structure, the way you've approached it is, okay, well, I'm going to add a new method to my data structure. So I have a map class, and so I want to add a put method. I'll add it directly to the map class. With graphs, we're actually going to do something a little different that is pretty common in the real world, which is rather than change our graph class itself, we'll create a separate class. So what we'll do is we'll, in a sense, decouple the algorithm from the type itself. So what we'll usually do is create a graph object. We'll pass that graph to some kind of graph processing method or constructor, and then we'll query the client class for information. So in other words, we take our graph and we pass it to this paths.java file that looks something like this. The paths class, it has a constructor where you give it a graph and an integer. It then, later, you can ask, is there a path to that vertex? And it will also give you that path. And we'll explore this idea a little bit more in the next video, but that's our goal. We're going to try and build a depth first search implementation to get an understanding really deeply of how this works. And even though we can run into a little trouble with depth first search, it's still going to be a very common tool, and let's explore how you actually build it.